All right, so let's get into the software transactional memory business. So last time we looked at Clojure as Lisp for the Java virtual machine, which I'm sure everyone was really excited about. Fewer parentheses, then regular Lisp, macros, tail recursion, interoperability with Java. I mean, unless you're a Lisp enthusiast, you probably didn't really care. What I care about is just one thing, and that is here the software transactional memory. So that's the topic of the day. So if you look at locking, so traditional old locking, you have multiple threads, they access a shared data structure, and in order to make sure that they do not damage the data structure, you use locks so that you achieve mutual exclusion in those parts of the algorithms that mutate the data structure. So if you have something adding something to the head of a queue, for example, the data structure needs to be mutated in some way, and you make sure that only one thread can do that kind of stuff at a time. And then you have to worry about how do you avoid deadlocks. And there's really no hard and fast rule for that, so then one can do it with some coding conventions, but they do happen often anyway. And of course, if people get the exclusion thing wrong, if they fail to do mutual exclusion, then you get these random bugs. So it's an error-prone thing. So the question is there some approach that does the right thing without programmers having to do all of this fiddly stuff? And so we've seen with actors, they had this way where they said mutations are, of course, the root of all evil. And if we have no mutation anywhere outside the scope of the individual actors, if there's no global data structures that can be mutated, then that's safe. But the disadvantage is then it's sometimes difficult to structure your program with these actors. You have to carefully think about how to decompose your program so that each of these actors has its own local memory, and that otherwise you have no global memory. So the transactional memory goes a different way. It says you can't avoid all shared data. There has to be some shared mutable state. But you can make it so that it's transactional. So if you think about what transactional means in a database, you of course can have multiple threads update the database, and the way you do it is you tell the database, here is the start of a transaction. You do your thing in the database, and then you say, here's the end of a transaction. And if another thread is trying to concurrently do the same thing, then it's up to the database to serialize those requests. And it's in database programming, people do this all the time. The databases are very good at parallelizing this. So if each of the requests works on different parts of the tables and it can be parallelized, it's up to the database to figure out that this can be so. The database is good in giving consistent views. If you do some modification and you then want to see the modification, then you get to see them. Someone else who does something different will not see your modifications until they're fully committed. So you have this big machinery around that shared database memory. And so the question is, can you do the same thing with good old RAM? Can you kind of have a database in RAM so that everything that's mutated is in that box, and that each thread then views a consistent state? And that's transactional memory. So you can really think of transactional memory as having a part of the memory as like this mini database. There are no manual locks. All you do is you say, do this part of stuff within a transaction, and that's the end of it. And so one of the ways you can think of it is it's like garbage collection for locks. So if you think of the bad old days in C++ when you had to manage your own memory, you called new, you called delete, and the penalty for messing up, for like deleting a block and then deleting it again, was that you would get subtle errors, many thousands of steps later, and it was really hard to debug. And so garbage collection solved all of that issue. It took the memory management away from the programmers on the theory that programmers cannot really be trusted with it. And you now know from the homework that programmers can't be trusted with concurrency either. So what if one takes it away? And so that's the approach that that STM takes. So in Clojure, they have various schemes of doing this, and we're only going to be looking at one of them. So they have thread local variables that are kind of like the variables, the immutable states that you can have inside an actor, which we're not going to be looking at. They have agents that where you can share stuff just like actors can send stuff from one place to another. We're not going to look at that either. We're going to be looking at this ref mechanism, and that is kind of the key hardcore transactional memory where you have synchronous sharing. You have a block that's accessed by multiple threads, but in a safe way. So every time you wanted to use that, you have to use this ref feature. And the only way you can update a ref is within a transaction. So we'll see an example pretty soon. Let's look, if you look at the typical example of a bank with multiple bank accounts, you might then have an array of refs. And when you update the first, then you make a transaction, you update the first one, you update the second one by, you move money from one to the other by the opposite amount, then you end the transaction, and then it all happens together. So the general vision that you should have is that something is a transaction, multiple references get updated all together, and you just wrap it in this transactional code bracket. So in a transaction, mutations are atomic, and that means that either all of them happen or none do. So if there's an exception that happens halfway through the transaction, then everything gets rolled back, just like you would have in a database. And you know this from database programming. It's a common thing, right? You issue some update, then you issue the corresponding update on another table. But if for whatever reason, for whatever tragic reason, you lose network connectivity to the database, Pluto is on the ascendant, whatever, then if an exception gets thrown, the database will roll back to the previous state. And so here the memory will do the same thing. So you can already tell that this is expensive, right? There has to be, someone has to save the old state of the ref until it's ready. So mutations are consistent. We'll see that when we look at these validators. They're isolated. Now that's an interesting thing. So let's say that I have two threads. Let me see if I can draw here. So I have two threads, and I have one of them updating this ref here. So this is some shared ref. And so they each do this in a transaction. So this one updates this ref. This one also updates it at the same time. And now, so we have an update. And now let's say this one here reads. And now let's say this one here, the second thread, does not yet update. The second thread just does a read on it. Then the second thread, when it does the read, it sees the old value. And the first thread, when it does the read, it sees the new value. See, for a read, you don't have to lock it. Anyone can read. But so the point is that they're isolated from each other. And that's, of course, important. So that each of them has a consistent view of the world, but it need not be the same view. So if you have some bank transactions and you are about to deposit something into an account from another account, then while that deposit is half in progress, like this guy here might be half done with the deposit, it can already see the new value. And the other thread will not see the new value until this one here is completely committed. So once you have a commit, then the new thread will see the committed value. The other thread. So that's an important property, the isolation property. Oh yeah, it'll make, so there is like the committed copy, the one after the last commit, and then when you enter a transaction, then for all you know, it might make a copy of the entire memory. It's up to optimize away from that drastic approach. So it should really, of course, only make copies of the variables that are being mutated. Yeah.
So
yeah.
So the reader will not be able to see the old value, right?
The reader will be seeing a consistent value whenever the reader started the transaction.
Okay.
Whatever was was the snapshot of the time, the reader is going to see that for the entire time of its transaction.
But during the transaction.
So when I say the reader, let's say this thing is the reader, T2 is the reader, and T1 is the writer, right? So when T2 starts some transaction to be able to get into the refs, at that point, the refs may be the new one or the old one, whatever they were, that's what it's going to see throughout the thing. Well, they can't probably yet be the new one because T1 hasn't yet committed. So they'll be the old one. T2 sees the old values, even though T1 already has written to them. So the other way of looking at it is that when T1 starts the transaction, it kind of temporarily gets a fresh set of values that it can operate on. Then when T1 commits, then they get updated, but that update does not affect T2's fresh set of values. Now what happens if both of T1 and T2 mutate? Right? Then you would have a typical race condition, and when the STM senses that, or for that matter when a database senses that, then both transactions fail and they get retried.
That will happen only if both of them try to commit at the same.
Right. So if it finds, so there has to be some exact interleaving thing, right? So what happened if T2 starts, then T1 starts, T1 does the commit, and then when T2 does the commit, at that point, so I guess T1 probably didn't fail. So here's what happens. So let's say T2 starts.
But T1 will.
Then T1 starts. T1 is done quickly and it commits. T1 is now the law of the land. Now T2 wants to commit, and then it has to say, wait a minute. It's just the other way where you can visualize this is from, where did this happen to you? In Mercurial? Right? And then it says, oh, now I have two heads. So it's exactly that kind of scenario. That at this point, the thing knows that I have two heads, it has sensed this interleave, and then except Mercurial just stays in that position, then it's up to you to clean up afterwards, which doesn't make sense in a fast-running piece of software. So in this case, T2 fails, it's going to be completely unrolled, and then it completely restarts.
But then what is the point? Because if there are all threads which are going to mutate, there is no point of having it concurrent.
If you have lots and lots of concurrent mutations on the exact same element, this is going to perform terribly. So that is very true. So if you have, so let's say you have an atomic counter and you have lots of threads, wanting to update that counter, this is probably going to be a lot of grief because they're all going to be ganging up on doing the update, and most of them are going to fail and then retry and try again. And so you need to avoid that situation when you want to use STM. And that's one reason why in this language, in Clojure, there's different approaches. They give you a separate type for atomic integers. They give you a separate type for actors, if that's the better model. But STM is a good thing for a part of your program.
What happens if there is a big hash table or something?
Yeah.
Let's say an array.
Yeah.
This guy T1 is trying to update only top.
It depends on how you structure it. If you say you have a ref that is the array, then you cannot up. Okay, I should back up here a little bit. There's no way in Clojure to do any mutation other than in a ref. So if you look at a data structure, say an array, there's no way of updating the ith element in an array. All you can do is you can replace the array with a different array that has a new value at the ith slot. So all data structures in Clojure are immutable. And so you wouldn't even have that situation. You can have an array of refs, but if you have a ref to an array, the only way to update that array is to replace it by a new array. Now it seems awfully expensive to say that every time you want to update one element in an array, that you have to do that. But it's kind of clever about it. What it does is you can think of it that instead of making a copy of the new of the whole thing, it keeps kind of a list of the recently changed things. And so it first consults that list before it goes into the big array. So an array is not just your array from CS1, but it's a more complicated data structure that has the same behavior. And then eventually it'll merge the changes in, and then of course you have to pay more cost, but it'll only make that when there have been lots of changes. So that the total cost per change is still constant time. So it amortizes the cost of propagating the changes in the data structure. So you get a data structure that looks like an array or like a map or like a list. And they're fairly complicated data structures because they have this the backbone of where all the information is, and then they have these more recent changes in some way where they can quickly look them up. The immutable data structures. Every time that you say change the value of this key, you get back a whole different map that now has the update. The old map still exists in case someone wants it, and in fact someone may want it in another transaction. That may be the other people's view of the world.
So when do you make this persistent?
Clojure doesn't have anything in particular to say, here's how when you say persist, okay, what do you say persistent? There's two ways of saying persistent.
Like in database, you will have, some people will have one view of database,
Yeah,
while other people who are mutating will have a different
Right.
view altogether.
right, that's the same thing.
When will all of them have the same view?
There's no particular way of making them all have the same view. Eventually.
But when all of them are trying to read, then they will have the same view, right?
Well,
Only
not
for
they will all have a consistent view. You have no good way of knowing what that view is. You just know that eventually, when all the transactions are done, and then the next transaction after that will happen, then they'll all see the same thing. But I mean, that happens all the time. You look at what happens at Amazon when people order stuff, and there's no way that Amazon knows at any particular time whether they're out of stock on a given item, right? They might have had 5 people buy it at that time, and it hasn't propagated in. And there's no way of saying, let's stop the business. Let's shut down the website for a few minutes until everything syncs. So it's the same thing. So, so the last thing that I said about that these transactions, they just get going, is what's called speculative execution. You also have this in database. In database, you can kind of choose which transaction mode you want. So speculative means we're just going to go ahead and do it. And then if we find out that it didn't work, then we'll back up. And this strategy, like I said, it works well on lots of reads and few writes. Now, it's of course absolutely important that you have no side effects inside the transactions other than the ones that you intended, because that whatever that code is inside the transaction can be executed many times.
Isn't it good for specific gaming
No.
applications where they want to speculate what the user will?
No. Speculative just means, as opposed to doing a safe way of doing a transaction, is that you're only allowed to start a transaction when no one else has already started one. That would be a safe way of having a transaction, right? You have like a global lock on something, and that way you would only have one transaction at a time. But that doesn't scale. So a speculative transaction, that's just a technical term for saying you're going to do the transaction. And if it doesn't work, then you're just going to retry. Sometimes they're called optimistic. I think that's actually the term that's used in databases, right? Because probably, the database vendors are worried, and if a manager listens in, then optimistic sounds better than speculative. All right, so let's look at syntax. So the way you make a reference, you use the ref construct. So ref together with some kind of a value here. Ref 42 makes a reference to that contains 42. So you should think of the ref thing as like a cell that points to some data item, in this case the 42. To get the value, you have to do a dereference. So one very reasonable way of thinking about it is like pointers in C or C++. It's a pointer to something that actually contains the data. Then to dereference the pointer, you use deref, and there's a syntactic shortcut. Here you can use this @ sign thing instead of deref. So you can think of that being exactly the same thing as asterisk of CNT in C, right? So whenever you want to do any kind of mutation, you have to put it inside a transaction. So you use this doSync. So doSync here is the transaction boundary. It's scheme, so you only have the closing parentheses here. And so inside here, you can use ref set, and that lets you update a value. So ref set takes the reference that you want to update, the new value, and then it's going to...
It's not going to point to a different value? It's just going to mutate the same thing?
It's going to replace. Okay, so okay, fine. I mean, you're saying this better than. Okay, so before we had 42. So actually, this is what's happening. It's going to make the 1729. Yes. So that is the correct picture. Very good. Now, of course, what often happens when you mutate something is you first get it. Then with a deref, right? You have to get to deref to get it. Then you have some kind of a computation that, and then afterwards you call ref set to change the same thing. And in order to do that more easily and more conveniently, you can use a different form. You can use the alter. So alter takes the variable, and then it takes the function that you want to apply to it. So over here, it's the +1 function. So here we're using the fact that plus is a function, and then when I do +1, it's automatically curried to give me the function of +1. So in this case, we're altering count by adding 1 to it. So in other words, I could also say alter count, and then in the more familiar syntax, plus %1. Which I have. Oh, I said down here I have it with ref set. Now, the general philosophy is you want to think about using alter instead of using ref set. First of all, it makes you think about transformations. It's a more functional point of view. You have some existing data. You wonder how you want to transform them. And of course, we don't usually do it on a single integer, but on some larger structure. And the other one is that oftentimes, when you have two threads that execute an alter, it doesn't really matter in which order they happen. One thread could do it, the other thread could also do it, and they could overlap that because the order doesn't really matter. And in a situation like that, you can use commute. So commute is a hint to the STM that the two transformations can be done in either order. So if I change the alter to commute, then one transaction can update, say, the count by 1. The other one can also update it by 1. And they can do it in either order while they're still within their respective transactions. And that works fine, provided that neither of the threads later looks at count. Because now they no longer have a consistent view. Right? With commute, you basically say, I'm going to make this change. I realize that someone else might also change this thing. So if I ever look at it again, I will turn into a pillar of salt. Right? So you have to, and that's not enforced, unfortunately, by the language. So that's something that the programmer has to enforce. So over here, now let's do this. For adding a value to a list. So I want to have two threads that add something to the head of the list. And so here, yeah?
So when I'm using commute and the two threads are changing the value,
Yes.
they have their own views, right?
Yeah?
So why are we assuming that we don't use CNT elsewhere in the transaction? I mean, even if we use it, we'll get our local value, right?
No, you don't.
That's the wrong thing to happen.
You don't know what you're going to get. So you can't use it afterwards anymore.
So what about the change that we made? Which one will be updated?
You don't know. That's why I say. So you don't want to. If you want to use a commute, then don't look at the value anymore. It's an optimization, but it's an optimization that's often very doable. All right. So let's look at this example where we add an element to the list. So here we're saying commute. We're modifying the list, and now here's the function here. So what we want to do is we want to cons the new item in front of it, and it just turns out that cons has the wrong order. Cons has first the item and then the list, and so if I want to do it the other way, and
No, it doesn't even have the list, right?
okay, how does cons work?
In scheme, it takes the value, new item, and then the list.
Yeah. Okay. So it takes the item. Okay. So actually, why do we need cons?
But here it's you're giving a list and then you're saying cons this new item to that list, right?
Well, the function here that it's gonna query this function. Okay, I'm gonna have to look at this. I don't see right now why I should have to use cons, because the cons should just work. It's queried the right way. Okay, I don't get it right now. It's a minor thing. All right, and so if something isn't commutative, then you don't want to do it. So over here, I'm having a cautionary example. Here, how can I show you this here? Where I first increment this counter, and then I later use the counter. And at this point, there's really no good way of knowing what might be happening. I say this operation here can commute with anyone else who wants to make the same update, and if someone else does make the same update, then I might see it.
So then here we are using the counter.
Yeah, so this is an example where you shouldn't be doing it. So
But then what is the use of doing the first step at all?
okay, it's often suppose I could do it in the other way around. So maybe I don't need this commute here. Or let's even say I do have this commute. Let's say I don't actually care in which order the elements are in the list, right? But I want them all to be distinct. Then I'm okay if I first add in count -1 and then increment. And in that case, I don't care in which order the increments happen, because I know they'll happen after they got inserted in the list. And I don't care in which order the insertions happen, so I'm okay with declaring them both as commutative. So again, remember what happens is that at these memory cells, they get these requests and say, I want to make this update. And so several of them may be bunching up. And so then the STM can reorder them in a convenient way, in whichever way it's convenient for it to make progress.
But won't the count be wrong if there are multiple threads? They will have their own.
Well, if all we want is that they're distinct, then commute will make sure that each of them is an atomic update, that each of them does a read, add, write, and so they will all be distinct values.
Okay.
And if that's our intent, then we're good. So the question is what you want to achieve here. Okay, it's an optimization, and I don't want to get too deeply into it. Same thing. I think we can live without validation. So let's get into this lab that actually shows this nicely, and I would like to have a bit of time for it. So I first, because I'll show you the program in Clojure, and it looks ugly in Clojure. So I thought it would be a good idea to kind of first show you what this program looks like in Scala, where it would look a little bit more familiar. So I have these vectors here that contain a bunch of numbers, and then I update these numbers in different threads, and then swap does something here. So you just read through this program in Scala and you run through it. It's pretty self-explanatory. And then you'll see what happens. Something goes wrong, and it'll be obvious what goes wrong, I hope. And then we'll do the same thing here in Clojure. And here you're going to be seeing a few unfamiliar functions, and I'm making you look them up so that you can be prepared for the homework where you have to go through the same thing. And it does the same thing. It does the swapping of different elements. But you can see there's a transaction here where it does an update inside the transaction. So figure out what that is, and then you'll see that it does the whole thing safely. And the code for it is actually quite simple. So just as an aside, I was pretty surprised when I did the homework solution for for this problem, how much shorter the Clojure program was than the Scala program. The Scala program was already pretty short. And it was not particularly hard to write once I wrapped my head around what it was that I wanted my transactions to be. Alright, let's do it and then we'll regroup after.